So now that you've been looking for a while for the pattern in Pascal's triangle, what number goes in here? 5. What strategy did you use to figure out that that would be 5? 1, 2, 3, 4, 5. Nice strategy. Good. How about this one? That's also 5. Did you use the same strategy? 1, 2, 3, 4, 5? Okay. Oh, someone else used a different strategy? Added the top numbers above it? Okay. Nice. How about this number? 15. And this one, 15 as well. What strategies did people use to figure out that that was 15? So some people are saying they noticed this pattern where these two numbers above add up to that number there. And there's symmetry in it, so that this one's 15. It looks like they're, if I drew a line down the middle here, everything on the other side is the same. Good. Other ways. This is what makes Pascal's triangle so fascinating. Yes? Okay. Nice. Went up 2, went up 3, went up 4, so we should go up 5. Nice. Okay. This row in particular is interesting because 1, 3, 6, 10, 15, those are called the triangle numbers. Have you ever heard of the triangle numbers? Triangle numbers are, if you take dots and you imagine that dot's a triangle, that's the first triangle number. If you then add 2 dots on the bottom of that, that's your second triangle number. See, it has 3 dots. And then the third triangle number. And then the fourth triangle number. And so the triangle numbers are actually just adding up your integers. Can you see that this one is just 1? This is 1 plus 2. This is 1 plus 2 plus 3. 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3 plus 4 plus 5. And so another way that you could have got that 15 is something in Pascal's triangle, depending where you're from. Some people might call it the sock identity. I like to call it the hockey stick identity. Is that if you start on any edge and go as long as you want and draw a hockey stick, all the numbers in the shaft of your hockey stick will add up to the number in the tip of the blade of your hockey stick. So the 1 plus 2 plus 3 plus 4 plus 5 equals 15. That works here as well. You can make a hockey stick backwards that way. 1 plus 4 plus 10, that equals 15. So you could get that 15 in a bunch of different ways. All right, next row. What does it start with? 1. So did anyone figure out this was 1 just because it always starts with 1? Yeah? Did anybody do the adding thing and say, well, it's 1 plus nothing, so that makes 1? So you could do that as well. 7, 21. Nice. So Pascal's triangle is fascinating. Well, I've shown you the hockey stick thing, how there's different patterns, how the triangle numbers show up in Pascal's triangle. I'm going to show you a couple other interesting things that happen in Pascal's triangle. How about if we added up the numbers in each row? This one's really easy to add up. You get 1. 1 plus 1, you get 2. 1 plus 2 plus 1, you get 4. What do you notice? They're all doubles. They're all powers of 2. So that's pretty cool that Pascal's triangles are all powers of 2. Yes? Yeah, and these are all multiples of 5. These are all multiples of 3, but not 6. These ones are all multiples of 7, so it's close, but not quite exactly. But it works for the even ones. So if you're just going through multiples of 3, multiples of 5, multiples of 1. Yes. What happens if we think of these numbers as actual numbers? 1, 11, 121, 1,331. Do you recognize those numbers? They're powers of 11. Sure enough, this is 11 cubed, this is 11 squared, this is 11 to 1, this is 11 to the 0, and this is 11 to the 4. Now we run into a problem with 11 to the 5. It is, though. If you think about going 1, 5, this is 10, which I can't put a 10 in there, but I'll put a 0 and carry the 1 over, making this 11. I'll carry the 1 over. And you get 11. 11 to the 5. Try that on your calculator. Is that 11 to the 5? Is 11 to the 6? 1, 6, 5. Carry the 1, 21. Carry the 2, 7. Carry the 1, 7, 1. Is that 11 to the 6? Well, this is a 1, this is a 6, this is a 5. I carry over the 1, making 21. So I write the 1. I carry over the 2, 17. Carry over the 1, 7. So that's pretty cool. And have you ever heard of the Fibonacci numbers? Sunflowers and all sorts of crazy stuff that the Fibonacci numbers are in. So these are the Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13. How do you find the next Fibonacci number? You add the two previous ones together. So 8 plus 13 is 21. Where do the Fibonacci numbers appear in here? Well, it's a little bit hard to see, and you might think I'm making stuff up, but all right. Ah, yes. How's that? Does that look good? That's a line. Do you see the Fibonacci numbers now? No? Okay, well, let's... Here we go. 1. 1. Whoa, whoa, whoa. 2. 3. Oh my goodness. I'm not supposed to move the whole thing. Here we go. I know I should, but I want to do it this way. Keep it. Oh, my line was a little bit off. This one has to be bent a little bit. There we go. That should be the one I clone. That's a better angle. Here we go. And the next one. Oh! 1 plus 4 plus 3, 8. I should, but this is more fun to. And that one adds up to 13. So if you have the right slope of line, you will hit the Fibonacci numbers all the way through. So, and we could get off topic on the Fibonacci numbers for another half an hour, but we have stuff to learn. So we do, right? And then if you wanted to keep making your Pascal's triangle bigger and bigger and bigger and shade in all of the even numbers, you get Sierpinski's triangle. But you can look up Sierpinski's triangle another time. So, have you ever seen Sierpinski's triangle? No? Okay. I'll show you something fun with Sierpinski's triangle. I don't have to put this on video. So once we notice that our combinations fit, we can now rewrite Pascal's triangle with combinations. 2, choose 0, 2, choose 1. And it's another pattern. 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3, and we can, and this will work all the way through with Pascal's triangle, which is pretty interesting. Now, where is this going and how is this? Well, obviously it connects to combinations, so that's why it's in this unit. But what is the binomial theorem, which is the next idea that we're going towards, and how does it relate? Well, the binomial theorem has to do with binomials. Okay? So what we're going to look at is what happens when we do binomials to different powers. So let's start with a plus b squared, something you already know. You know how to square things. What is this equal to? It's equal to a squared plus 2ab, good, plus b squared, good. Can you do a plus b to the 1?
A plus b.
It's a plus b. What is a plus b to the 0? 1. Can I add these coefficients in green for you, even though you don't have to write these ones? Can someone tell me what a plus b cubed is? You don't like this? This is scary looking?
A cubed.
It's going to be a cubed
Plus 3ab.
plus 3a squared. Oh, I'm going to make that 3.
Oh, yeah. 3a squared.
3, and it happens to be a squared b plus 3 ab squareds plus b cubed. It's all right if I add those ones in there. Ooh. Oh my goodness. A to the 4, let's... Now, you could have done a plus b cubed the old school fashioned way, right? Which means a plus b cubed is a plus b times a plus b times a plus b. And you already knew a plus b was a squared plus 2ab plus b squared. And then you go zoo, 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 zoo.
It's b squared, not.
Yeah, that's right, that little 2. Just erase it. Q. Okay, and then you multiply all that through and you're going to get a cubed plus 2a squared b plus ab squared plus ba squared plus 2ab squared plus b cubed. And then you put your like terms together. And you've got an a squared b there and another a squared b there. So that'll give you 3a squared b. And you've got an ab squared there and an ab squared there. 3ab squared plus b cubed. Whew. So we could use the old school way, or if you start to notice a pattern, what's going to be a plus b to the 4?
A to the 4th.
A to the 4th.
Plus 3a squared b squared. Plus 4.
4a cubed b plus
4.
6 a squared b squared
Plus 4. ab squared. 3.
Now, why does that work? Okay? Well, when you're multiplying a plus b to the 4 out, what you're doing is having a plus b times a plus b times a plus b times a plus b, basically a plus b times by itself 4 times. Now you've learned how to FOIL or distribute when you have two of them, right? Every letter gets every letter. Now when you're multiplying this whole thing out, you have to think about every combination possible. For example, you could multiply the A times the A times the A. Right? That will give you your A to the 4. You could multiply your A times your A times your B times your A. That will give you an A squared. Oh, no, I got them all. That will give you an A cubed and a B. Okay? All the way through, you have A's and B's, and you're trying to figure out, well, how come there are 4 A cubed B's? And why does that match up, this number 4, match up with 4 choose 1? Well, one way that you can think of it is you can say, well, if I wanted to choose exactly one B, and I'm multiplying this through, well, that would mean I'd have to multiply 3 A's and 1 B. How many B's could I choose if I'm choosing just one of them? 4 choose 1. Because I could choose this B, I could choose this B, I could choose this B, I could choose this B. If I chose this B and multiplied it by the other 3 A's, I would get 1 A cubed B. If I choose this B and multiply by the other 3 A's, I'd get another A cubed B. And there's going to be 4 of them. So why is there 6 A squared B squareds? Well, this number here is 4 choose 2. And if I look at how I could choose my B's, and I'm using B's because it's matching up with the numbers starting here at 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. But 4 choose 3 is the same as 4 choose 1. So choosing 3 A's is the same as choosing 1 B. So when I'm figuring out this 6 for 4 choose 2, I need to have 2 B's. I have 4 B's to choose from. How many different ways can I make groups of 2? Will be 4 choose 2. And so the binomial theorem, when you're multiplying things out, multiplying binomials out, combinations appear. So our next part of the unit is dealing with Pascal's triangle, which connects to the binomial theorem, and looking at this pattern and how we can use this pattern to multiply things out that would otherwise take a long time. Like A plus B to the 4, if you had to multiply that out,
Yes.
there'd be a lot of multiplication you'd have to do. This is faster. Okay, but then we're going to have to learn strategies for when we add more numbers to it.